A fragment of composite material lies on a sterile lab table, salt-scored, sun-bleached, warped by months, maybe years, at sea. A technician adjusts a light. The carbon fibers shimmer. Not random damage, not chaotic tearing, a pattern. If an aircraft struck the ocean at high speed, if it broke apart instantly, if it fragmented into thousands of pieces at the surface, why does this piece look different? What did China's debris analysis of MH370 actually conclude? Did it support a high-speed dive? Did it suggest a controlled descent? Or did it quietly point somewhere in between? For years, headlines simplified it, speculation amplified it. But buried inside technical assessments, inside fiber fracture angles, honeycomb compression signatures, and hydrodynamic scoring, was a more measured story. Tonight, we slow down. We examine what was actually analyzed, what was inferred, and what remains uncertain. Because when composite panels tell a story, they whisper in physics, and physics rarely lies. The aircraft vanished from civilian radar in the early hours of the morning, transponder silent, voice contact lost. Primary radar returns fading into darkness. Days later, satellites revealed a series of automated handshakes, hourly digital pings that mapped a lonely arc across the southern Indian Ocean. No confirmed wreckage field, no cockpit recordings, no flight data recorder, just signals, models, and eventually, debris. When fragments began washing ashore years later, multiple nations examined them. Among them, China. Their focus? Structural behavior, impact mechanics, failure signatures embedded in carbon composite. But here's the tension. If the debris suggested a vertical, high-energy impact, that aligns with one theory. If it suggested controlled ditching or shallow descent, that aligns with another. And if the debris showed mixed signatures, then the narrative becomes more complicated, which is exactly what appears to have happened. Because debris is not just wreckage, it is frozen motion. Each torn fiber records force vectors. Each crushed honeycomb cell preserves deceleration rates. Each layer separation encodes stress direction. In the absence of cockpit data, debris becomes the black box. And when a nation conducts its own structural assessment, using its own labs, its own analysts, its own fracture modeling, those conclusions matter. Not because they settle the mystery, but because they narrow it. Did the structural evidence support a pilot-controlled glide to the ocean? Or an uncontrolled, fuel-starved plunge? Or a third scenario we haven't fully modeled? The answer is not cinematic. It is technical, measured, conditional, and that is precisely why it's so powerful. If you're drawn to the evidence, not just the headlines, if you care about what the data actually says, rather than what trends, then this channel is built for you. Subscribe and stay with this investigation. Like the video if you value deep, careful analysis over noise, and in the comments, tell me something specific. Do you believe debris alone can meaningfully reconstruct an event this complex? Or does it only narrow probabilities? Your insights matter here, because this isn't about spectacle, it's about understanding. And in the next chapter, we rewind to the moment debris entered the equation, when ocean currents became couriers of evidence, and the search area began to shift. The ocean is empty, not metaphorically, literally. A search grid stretches across millions of square kilometers of the southern Indian Ocean. Wind shear, swells, abyssal plains descending more than 4,000 meters. This is where models suggested the aircraft's final arc ended. But here's the problem. For more than a year after the disappearance, there was no confirmed physical evidence. Only satellite handshake timing offsets. Only Doppler shift modeling. Only probabilistic corridors. Then, months later, something changed. A fragment washed ashore. Not near the search zone, not near the projected arc, thousands of kilometers away. Oceanographers began reconstructing surface current vectors. Using historical drift data, seasonal monsoon patterns, and floating object simulations, they modeled backward trajectories. If debris entered the water along the southern arc, and if currents followed seasonal pathways, Then fragments could plausibly travel westward toward African coastlines. That was the first bridge between signal theory and physical reality. And then more pieces appeared. Composite panels, interior fragments, control surface components. Each one became a question. Where exactly did it separate from the airframe? At what altitude? Under what force profile? Because location of discovery does not equal location of impact. Ocean drift is not linear. It is chaotic, but statistically predictable. This is where China's role becomes significant. A substantial number of passengers on board were Chinese nationals. From the beginning, there was national urgency, political, emotional, technical. When debris was recovered and distributed for examination, Chinese aviation and materials specialists conducted independent structural assessments, not to rewrite the global search, but to evaluate what the material itself implied about the final moments. Let's compress the sequence. Aircraft disappears from civilian radar. Military radar tracks a turnback. Satellite handshake data defines a southern arc. Massive seabed search begins. No wreckage field located. Months pass. First confirmed debris washes ashore. Additional fragments recovered over subsequent years. Structural analyses initiated across multiple labs, including Chinese institutions. Each fragment was photographed, measured, microscopically examined, layer by layer evaluated, and this is critical. The goal was not to solve the disappearance in one stroke. The goal was narrower. Determine whether structural signatures were consistent with A. High speed, nose-down impact. B. Controlled descent with flaps deployed. C. Mid-air breakup before ocean contact. 3 very different physical scenarios. 3 very different energy distributions. If debris supports a vertical high-energy plunge, that suggests fuel exhaustion and uncontrolled descent. If debris supports low forward velocity and flap deployment, that suggests human input at the end. If debris supports mid-air separation, that suggests an earlier catastrophic event. Each pathway changes everything. Search zones, responsibility, safety protocols, public understanding. And here's the tension. Debris rarely tells a clean story. It tells fragments of force. It tells pieces of sequence. But it does not narrate intention. So what exactly did the Chinese analysis emphasize? Did fracture patterns indicate upward hydrodynamic pressure from below? Did honeycomb compression ratios suggest high deceleration? Did hinge points show overload from aerodynamic stress before impact? Or did certain panels show minimal leading edge crushing, implying reduced forward velocity? These are not dramatic questions. They are mechanical ones. But mechanical truths carry enormous narrative weight. Because if the structure whispers high energy, while drift patterns whisper intact entry, then something doesn't align. And misalignment is where investigations deepen. In the next chapter, we step inside the material itself. Carbon fiber, resin matrices, honeycomb cores. We examine how composite aircraft structures fail, and how those failure modes become silent witnesses. Because before we interpret China's conclusions, we have to understand the language the debris speaks. Not metal, not solid, but layered. Carbon fiber skins, epoxy resin matrix, aluminum honeycomb core. Light, strong, engineered to flex, but within limits. Now imagine that structure meeting the ocean at 800 kilometers per hour. Water is fluid, yes. But at high velocity, it behaves like concrete. So what happens? Composite materials don't crumple the way aluminum does. They fracture in patterns. Fibers snap along load vectors. Resin delaminates between plies. Honeycomb cells compress in distinct geometric collapse modes. Each failure mode corresponds to force magnitude and direction. 1. Delamination. Layers peel apart under shear stress. 2. Fiber tensile break. Fibers snap under extreme tension. 3. Core crush. Honeycomb collapses under compressive load. 4. Skin buckling. Outer layer wrinkles from uneven pressure. If an aircraft impacts vertically at high speed, we expect extensive leading-edge crushing, symmetrical compressive signatures, high-energy fiber shattering, severe honeycomb compaction. If it impacts at lower forward velocity, more controlled, we expect partial skin separation, less uniform crush depth, hydrodynamic tearing from beneath, possible intact sections separating later. And if breakup occurred mid-air, we would expect aerodynamic overload fractures, tears consistent with airflow forces, not water resistance, different signatures, different physics. Chinese structural specialists reportedly focused on two key debris characteristics: fracture surface morphology, core compression depth and pattern. Let's unpack that. Fracture surface morphology is the microscopic texture of broken composite. Under scanning analysis, fiber ends reveal whether they failed under tension, compression, or bending. Tension failures look clean and elongated. Compression failures appear crushed and splintered. Shear failures show angled tearing. It's forensic physics, and honeycomb cores, they're even more revealing. If water pressure crushed the core from beneath during a flat impact, compression patterns would differ from a nose-first plunge where force travels longitudinally. In simplified terms, impact angle leaves a geometric fingerprint. Now pause, because here is where interpretation becomes delicate. Some early narratives suggested a steep, high-speed dive, an uncontrolled descent after fuel exhaustion. If that were true, structural fragments would likely show extreme deceleration forces, uniform leading-edge trauma, severe fragmentation, but certain debris pieces recovered did not display uniformly catastrophic crush patterns. Instead, some showed partial structural integrity along specific edges. Does that mean the aircraft ditched intact? Not necessarily, because ocean impact is chaotic. Hydrodynamic forces redistribute unpredictably. Large airframes can break apart in milliseconds, with sections experiencing wildly different loads. One fragment might show violent compression. Another, meters away, may show relatively modest shear separation. Absence of total pulverization is not proof of controlled descent, but neither is partial crush proof of vertical plunge. This is the narrow line investigators walk. Imagine throwing a laminated ice sheet onto water. If you throw it flat and slow, it flexes, cracks irregularly. If you slam it vertically at speed, it shatters violently. But if it hits at an angle, partially rotating, some sections shatter, others shear cleanly, others survive briefly before secondary breakup. Real-world impacts are rarely textbook. So what did the fracture signatures most closely resemble? Predominantly tensile overload from aerodynamic stress? Or compressive hydrodynamic crush? Or a mix, suggesting transitional dynamics during impact? Did core compression depths align with terminal velocity models? Or were they more consistent with reduced forward speed? And most critically, were control surface components consistent with flap deployment at impact? Because flap position changes airflow, it changes descent profile, it changes impact geometry, and flap position leaves mechanical traces. Available reporting suggests the Chinese analysis did not definitively endorse a controlled ditching scenario, but it also did not conclusively validate a perfectly vertical, nose-first plunge. Instead, interpretations appear to indicate complex breakup behavior consistent with high-energy ocean impact, without sufficient evidence to confirm pilot-controlled final approach. In other words, the material evidence narrowed possibilities. It did not eliminate ambiguity. That is important, because ambiguity is not weakness in science. It is honesty. If the debris does not cleanly support a textbook suicide dive and does not clearly support a calm glide to the surface, then what exactly happened in those final seconds? Did the aircraft enter a spiral? A phugoid oscillation? A partially controlled descent degrading into stall? Or did hydrodynamic chaos simply obscure what would otherwise be obvious? The mechanism gives us constraints, but constraints are not conclusions. In the next chapter, we shift from composite physics to human consequence, because behind every fiber fracture and compression ratio were families waiting for certainty. And the interpretation of debris is not just technical, it is deeply human. A departures board frozen in time, flight number, status, delayed. then later, blank. In laboratories, technicians examine fracture lines under magnification. But thousands of kilometers away, families examine something else. Silence. Because while engineers debate compressive load paths, parents, spouses, children measure time differently. Not in newtons, not in deceleration rates, in unanswered calls, in birthdays passed, in hope recalibrated year after year. A significant portion of the passengers were Chinese nationals. From the earliest hours, public pressure intensified domestically, demanding transparency, demanding answers, demanding accountability. And this is where debris analysis becomes more than structural science. When fragments were confirmed, they did not just represent physical validation of ocean impact. They represented closure, partial, fragile, incomplete, but closure nonetheless. Because for years, there was a haunting possibility. What if the aircraft was somewhere else? What if the arc was wrong? What if the modeling failed? Debris confirmed at least one hard truth. The aircraft entered the ocean. Not a hidden runway, not a covert diversion, the sea. But confirmation of impact is not confirmation of how. And that difference matters deeply to those left behind. Imagine being told, the structural signatures suggest high energy impact. What does that mean to a family member? Does it imply suffering? Was it instantaneous? Was there awareness in the final seconds? Engineers avoid these questions, not because they lack empathy, but because their discipline deals in materials, not consciousness. Yet every fracture pattern carries emotional gravity. If analysis suggested a rapid, uncontrolled descent, families might infer chaos. If analysis suggested controlled glide, they might imagine intention. And intention changes the narrative of loss. That is why interpretation must be careful, measured, evidence-bound. Because a conclusion, once spoken publicly, does not remain technical. It becomes human. Modern aircraft are extraordinary machines. Redundant systems, triple-channel flight computers, satellite communication links, autopilot logic designed to smooth turbulence you barely feel. And yet, remove fuel, remove communication, remove active guidance. Gravity reasserts itself. There is a stark contrast here. Human trust in systems. Systems subject to physics. The debris does not accuse. It does not assign motive. It does not narrate the cockpit. It simply reflects the final transfer of energy between machine and ocean. One of the most sensitive aspects surrounding the disappearance has always been the question of agency. Was there deliberate action? Was there incapacitation? Was there system malfunction cascading into unrecoverable descent? Chinese debris analysis did not, and likely could not, resolve agency. Structural data cannot confirm intent. It can only define envelope. It can tell us, this level of force occurred. This direction of stress applied. This compression magnitude suggests deceleration of X range, but it cannot tell us who was at the controls, or whether anyone was. For a moment, imagine the final minutes. Dark cockpit, autopilot disengaged or still engaged. Fuel gauges approaching zero, engines spooling down one by one. We do not know the exact configuration. We do not know the crew state. We only know that somewhere along that southern arc, the aircraft transitioned from controlled flight to ocean impact, and fragments began a slow drift westward. Years later, those fragments landed on distant shores, carrying silent testimony. For families, the core question is simple. Was it quick? For investigators, the layered questions are more complex. What was the descent rate? What was the bank angle? Were flaps extended? Did aerodynamic stall precede impact? And here's the uncomfortable reality. Debris analysis may constrain some of these possibilities, but it cannot answer them fully, which leaves space. Space for speculation, space for alternative theories, space for unresolved tension. Because once you acknowledge what debris can tell you, you must confront what it cannot. 3 pathways, 3 narratives, 1 set of debris, and here's the tension. China's debris analysis did not exist in isolation. It entered an already polarized landscape of interpretation. So what do the main theories look like when filtered through structural evidence? Let's break them down. Theory 1. Uncontrolled high-speed descent. In this scenario, we expect high vertical velocity, severe leading-edge crush, extensive fragmentation, deep honeycomb compression. Pros: consistent with fuel depletion modeling, aligns with absence of controlled radio communication near end of flight, compatible with high-energy impact physics. Constraints: some recovered fragments did not show uniformly catastrophic crush signatures. Certain control surface components appeared less severely deformed than extreme vertical models predict. Now pause. Does that mean the vertical dive model is wrong? Not necessarily, because fragmentation in ocean impact is non-uniform. Sections shielded by airflow geometry or separated milliseconds earlier can experience reduced force loads. High energy does not guarantee identical damage everywhere, but it raises questions. Theory 2. Controlled descent/ditching attempt. In this scenario, we expect lower forward speed at impact, more distributed breakage, potential flap deployment indicators, less uniform compressive crush. Pros: some debris showed limited leading-edge compression. Certain sections retained partial structural integrity. Flaperon recovery led some analysts to question whether control surfaces were extended. Constraints: successful ditching of a wide-body aircraft in open ocean at night without engine power is extraordinarily difficult. Even controlled descent would likely result in rapid breakup in heavy seas. No intact fuselage sections have been located. And here is the key nuance. Chinese structural interpretations, based on available reporting, did not definitively confirm flap deployment at impact. Without mechanical actuator position confirmation, inference remains limited, which means controlled descent remains possible, but not proven. Theory 3. Mid-air breakup. In this scenario, we expect aerodynamic tearing signatures, in-flight overload fracture patterns, broad debris field at sea surface. Pros: would explain distributed debris drift patterns, would reduce need for high-energy water impact interpretation. Constraints: satellite handshake data suggests sustained flight for hours after initial disappearance. Recovered fragments do not strongly indicate classic explosive decompression signatures. No confirmed evidence of in-flight fragmentation before final descent. This theory remains the least supported by structural evidence currently available. Here's the paradox. If debris shows high-energy impact signatures, that supports uncontrolled descent. If debris shows areas of limited crush, that invites controlled descent speculation. But both can coexist in a chaotic impact event. Ocean entry is not binary. An aircraft can descend steeply, then rotate, then yaw, then strike asymmetrically. Milliseconds matter, angle matters, sea state matters, and models, no matter how sophisticated, operate within assumptions. Compression depth measurements, fiber fracture microscopy, impact vector simulations, drift path modeling. None of these alone determine intent. None determine consciousness. None determine motive. They define physics, and physics defines boundaries. China's debris-focused assessments appear to fall within those boundaries, supporting high-energy ocean impact as likely, while not definitively resolving descent configuration. Measured, technical, non-conclusive, which, for some observers, felt unsatisfying. Because after years of mystery, ambiguity feels like absence. But in science, ambiguity is data-limited reality. If high-energy impact is more probable than gentle ditching, then why has the main wreckage not been conclusively located? If models constrain the southern arc, then how can debris analysis refine that corridor further? And here is the pivot. What if reinterpreting debris does not answer how alone? What if it reshapes where? Because Chapter 6 is not about what the material concluded. It's about what those conclusions imply for the search itself. If impact was extremely high energy and near vertical, debris dispersion might be tighter, initially concentrated before ocean currents distribute fragments. If impact involved forward velocity and rotational breakup, debris could scatter more broadly across the surface before sinking. And that difference, meters per second, degrees of pitch, scales into kilometers of drift uncertainty over years. Oceanographers rely on reverse drift modeling. Take a fragment's discovery location. Run current models backward in time. Estimate likely origin zones. But here's the hidden variable. Initial breakup behavior affects surface float time. If certain components detached immediately and remained buoyant longer, their drift paths widen. If other components sank quickly before resurfacing, their drift origins narrow. So when structural analysis suggests complex breakup rather than a single intact plunge, it injects variability into drift reconstruction. Not chaos, but uncertainty bands. And uncertainty bands expand search corridors. Every search model rests on assumptions. Descent rate, impact angle, fragmentation timing, flotation duration, seasonal current variability. Change one assumption slightly. The predicted crash zone shifts. Change two. It shifts dramatically. China's debris-focused conclusions appear to reinforce high-energy impact as probable. But high energy does not mean perfectly vertical. And that nuance matters, because a descending aircraft in a spiral, or partial bank, may enter water offset from projected final arc extrapolations. Milliseconds before fuel exhaustion, kilometers beyond estimated endpoint. Tiny deviations at 35,000 feet become vast separations at sea level. Consider this. Satellite handshake data defined an arc, but not a point. Fuel modeling defined a likely exhaustion window, but not an exact second. Structural debris suggests high-energy ocean impact, but not a precise vector. Each dataset narrows probability. None deliver coordinates. And when layered together, they create something powerful but incomplete. A constrained uncertainty. For nearly a decade, vast portions of ocean floor have been scanned. Sonar sweeps, autonomous underwater vehicles, deep tow imaging systems, and still, no confirmed main wreckage field within the primary search zone. So the question becomes sharper. If debris supports high-energy impact along the southern arc, why hasn't the aircraft been found there? Two possibilities emerge. One, the models are broadly correct, but the seabed terrain concealed the wreckage beyond current survey resolution. Two, one or more assumptions in descent modeling were slightly off, shifting the true resting site beyond searched boundaries. And this is where debris analysis subtly reshapes the future. If the final descent involved instability, oscillation, roll, partial aerodynamic stall, impact coordinates could deviate laterally from projected endpoints. If impact angle varied, debris drift modeling recalibrates. If fragmentation timing differed from initial assumptions, float paths change. None of this overturns established findings, but it widens margins, and margins matter in ocean search mathematics. This is no longer just about one event. It's about how we investigate disappearances in the satellite era, how we integrate space-based telemetry, ocean current modeling, structural fracture science, probabilistic search algorithms, and how we communicate uncertainty publicly. Because premature certainty erodes trust, but endless ambiguity erodes hope. China's debris conclusions, measured, technical, non-definitive, sit precisely at that intersection. They do not confirm controlled ditching. They do not definitively prove vertical dive. They support high-energy ocean impact as likely, while leaving descent configuration unresolved. And that unresolved detail continues to echo.